Hi, hello, I'm Kiran Kumar from Nature of Physics and Art. Welcome to my channel. Today's topic is electric dipole, in which first difference between the electric dipole and magnetic dipole. After that, continuation only, that is torque acting on a electric dipole placed in a uniform electric field. Okay, and part 2, part 3 videos about the electric dipole. Part 2 is that is potential energy of the electric dipole in a uniform electric field, and third, that is work done on the electric dipole in a uniform, and fourth one is time period frequency of the electric dipole placed in a uniform electric field. Like that, I will do the videos from the electric field and charge. So this is completely about the electric dipole part 1 part 2 videos. Okay, see, first, what is electric dipole? Electric dipole is a system of two equal and unlike charges are separated by small distance. So this is minus q charge and this is plus q charge, separated by a small distance. This is called electric dipole. A system of two equal and unlike charges are separated by small distance is called electric dipole. So here O is the center of the electric dipole, and center to the negative charge is a distance, and center to the positive charge also a. And here Q is the charge. Charge, and to a small distance, that is small distance, and charge SI units is coulomb. And next, comparing with the magnetic dipole. So this is the magnetic dipole that has the north pole and south pole, and pole strength is taken as M. This is the north pole strength and this is the south pole strength. So taken here, this is the south and this is the north. And length of the magnetic dipole is 2L. From the center to the south pole is L, from the center to the north pole also L. Here small m is the pole strength. So what is the pole strength? The ability of attraction or repulsion of the magnetic substance is called pole strength. The ability of attraction or repulsion the magnetic substance. See, and it is a scalar quantity. SI units are, even charge also scalar quantity. SI units, that is ampere meter for the pole strength, for pole strength. So SI units of M, here I am writing like this, SI units of M. So that is ampere meter. Try to understand. Same we can compare with the magnetic dipole. And directions we can discuss. Directions, here electric dipole direction is from the negative charge to the positive charge, inside. And here also the direction is inside, from the south pole to the north pole. Direction is from the south pole to north pole. And outside direction is from the north pole to the south pole. North pole to the south pole. Here also even outside the dipole, electric field direction from the positive charge to negative charge. Simply releases from the positive charge, enter towards the negative charge. See, next, that is electric dipole moment. Electric dipole moment. Indicated letter is capital P. So capital P, which is equal to product of charge and length of the electric dipole. What is the dipole moment of electric dipole? That is product of charge and length of the dipole. Charge is Q and length is 2A. And what is the SI units? It is a vector quantity. So it is a vector quantity, and SI units of P, which is equal to charge is coulomb and distance is meter. So coulomb meter. And here we can discuss the magnetic dipole moment. So magnetic dipole moment, indicator letter capital M or small mu also. Okay, capital M is also product of pole strength and length of the magnet. Here product of charge and length of the magnet. In the magnetic dipole moment, okay, that is product of pole strength and length of the magnet. Okay, so it is a vector quantity. It is a vector quantity. Okay, and SI units of capital M is ampere meter and meter. So small m is ampere meter and length is meter. So ampere meter square SI units. Okay, so this is the difference between the electric dipole and magnetic dipole. Just a second, I will clean the board. See, continuation. Now torque acting on a electric dipole which is placed in a uniform electric field. This is the uniform electric field. See, now electric dipole is initially perpendicular to the electric field, then it is naturally rotate in the direction of electric field. So initially perpendicular to the electric field and it is rotating in the direction of electric field. That is natural rotation. So first I am taking here dotted lines of the electric dipole like this. Okay, here theta 1 which is equal to 90 degrees. Theta 1 which is equal to 90 degrees. That is perpendicular to the electric field. Electric dipole is perpendicular. Okay, now it is rotating like this. Okay, so the dipole is making certain angle, okay, with the electric field, that is theta 2. So theta 2 which is equal to, here I am considering theta, certain angle, final angle. Okay, and finally comes to the in the direction of electric field. But before coming to the electric field direction, just we are taking final angular displacement, that is theta 2 is equal to theta. Okay, so this is the positive charge, this is the negative charge. So here force is acting F. Okay, here also force is acting, that force is taking like this F. Okay, here the F which is equal to plus Q into E. So what is the electric field intensity formula? E is equal to F divided by Q. From this equation, F is equal to Q into E. So this is the negative charge. That's why here force F is equal to minus Q into E. Here force F which is equal to plus Q into E. So separately I wrote force value here and here. Here negative charge, that's why negative sign taking. Here positive charge and positive sign is considering electric field is force per unit charge. Just a second. And think O is center here and this is the length of the electric dipole. So length of the electric dipole is 2A. 2A is the length of the electric dipole. Okay, so here how many forces are acting on that? Two forces are acting. So these two forces are both are acting at the different point and opposite in direction. If both are acting at same point, then get cancelled. Reason is both are equal in magnitude, opposite in direction. But here both are equal in magnitude, opposite in direction, but takes place at two different points. Nothing but there is a perpendicular distance. I can draw the diagram. Same. See, this is okay, electric dipole. This is the positive charge, negative charge, and this is the positive charge. Here force is F is equal to plus QE, okay, just a second, plus QE, okay. Here force acting like this, that is F is equal to minus QE, okay. These two force form the torque, that is couple acting on the electric dipole. So that we are considering torque. Torque is the formula force into perpendicular distance. See, this is the point is A, and this is the B point, and this is the C, and here BC is the perpendicular distance of the two forces. Okay, so now here torque, which is equal to force into perpendicular distance. Okay, now torque, which is equal to force is F into perpendicular distance is BC. So F is equal to QE here, but F is equal to QE, and we have to find the BC. This is the making an angle theta. Here also we can take theta. Okay, so for this sine theta, which is equal to, that is opposite is BC divided by hypotenuse is 2A. This is 2A. So 2A. So here BC value we got 2A sine theta. Okay, so the value is replacing, okay, BC, which is equal to 2A sine theta. Okay, now torque, which is equal to QE into 2A sine theta. So tau, which is equal to Q into 2A E sine theta. So here P is the electric dipole moment, P, which is equal to Q into 2A. So tau, which is equal to PE sine theta. This is equation number 1. So direction in vector form, tau bar, which is equal to P bar cross E bar. This is the second equation for the torque acting on the electric dipole, which is placed in a uniform electric field, and 3 applications are there, cases that I will continue just a second. And continuation cases based on the, okay, torque tau is equal to PE sine theta. Okay, first one, if theta is equal to 0, okay, so then sine 0 is equal to 0, then tau is minimum, which is equal to 0. Okay, and second one, if theta is equal to 90 degrees and sine 90, which is equal to 1, so tau is maximum, so which is equal to P into E. So sine 90 is equal to 1. Here first one is sine 90 is equal, sine 0 is equal 0, 0 into anything 0. Okay, here 1 into PE, that is PE. So P is the electric dipole moment and E is the electric field. And third also, that is if theta is equal to 180 degrees. So what is takes place here, that is sine 180, which is equal to 0. So then tau minimum, which is equal to 0. So last case is not necessary. Mostly First one, second one only we consider. Okay, thank you very much. I will continue with part 2 video, that is potential energy of the electric dipole placed in a uniform electric field. Okay, see you soon.